All right. Everyone ready for some databases? Woo! Yes. Good. So this is one of my favorite subjects in all of databases because it just illustrates how cool, how easy it is to think about questions when you have some idea of what it means for two answers to be equivalent, and kind of helps you understand how to pivot your question in order to answer it better. But before I get into that, I ran out of time last lecture, so I just want to cover the couple of things that I missed and recap what we were talking about towards the end of the last lecture. And the first thing there was implementing joins. Whoa, funky. The first thing there was implementing joins, and my screen is being funky. Let's try that again. All right. So, what we left off on was this idea that you could implement a join in a couple of different ways. And the first and probably easiest way of doing this was the nested loop join that we talked about way back several weeks ago. The other thing we talked about way back was this idea that you could take a nested loop join and break it down into chunks. Break down each data set into chunks, load each chunk independently, and in doing so, reduce the amount of I/O and computation that you needed to do. Now, what we didn't discuss at that point was the fact that you could take advantage of certain properties on the data, on the join specifically, to make the join more efficient. So what we talked about last class was this idea that you could, if you were processing an equality join specifically, you could organize the data that you were taking as input before you actually tried joining it. And by doing a little bit of organizational work before you actually perform the join itself, you could make the join run faster. Now, what I skipped over last class was this idea, was one particular way of doing this, which is typically called a sort merge join. So, loosely put, a sort merge join assumes that your input data is sorted. If it's not already sorted, you need to sort it before you can perform a sort merge join. Now, in order to do a sort merge join, you start at the head of the list and look at every single entry. And anytime you find two entries that match, you emit them. And if the top two entries don't match, then you move whichever cursor is lower than the other. So in this case, we're starting off at the very top. Both cursors are pointing at record 1. And because they're both pointing at record 1, we can join those two tuples together. Now at this point, we move both cursors ahead. And now they're pointing at 2 and 4. 2 and 4 are different. So, well, nothing gets produced immediately, but we can move one of those cursors ahead. So if we move the cursor that's pointing at 2 ahead, then, well, eventually we might hit a 4. It's always safe to move the lower cursor ahead because we know we're never going to join against a value that we've hit with the higher cursor. So in this case, 2 is less than 4. We can move the cursor for 2 ahead. We can keep moving it ahead until we hit another value that's greater than 4, in this case 5. Now, 4 is the lower cursor. We know that that there is no record in A that could possibly join against 4, so we can move that cursor ahead. Move that to the next cursor. Lo and behold, we find a 5. Great, those two match up. We advance both cursors, and now one of the two cursors hits the end, so we're done. So this basically takes advantage of the fact that whenever we're looking at one of the two cursors that's bigger, we know that we've gotten to that point. We know that there's no possible thing in the other relation that could have joined up to that point. And so as long as we keep advancing the smaller of the two cursors, we know we're never going to encounter a possible join that we haven't encountered. So, question. What's the time complexity of this? Assuming my inputs are already sorted, what is the time complexity here? N. Why? It only has to do one scan through both of the tables. You're never going to touch a single record more than once. And because of that, this is one of potentially the most efficient join algorithms that exists. Assuming that we needed that the data wasn't already sorted, what would the time complexity be? N log n. So the cost of doing a sort is n log n. With that overhead, it's still a pretty efficient sort mechanism. There's also one other kind of cool thing about this particular algorithm. Assuming that the data is already sorted, unlike any of the other algorithms that we've looked at, this is what we call a pipelined algorithm, a fully pipelined algorithm. So this kind of came up briefly when we talked about selection and projection. If I want to produce one tuple out of a selection or a projection operator, how many tuples do I need to read in? Projection is easier. How many tuples do I need to read in if I want to produce one tuple in the output of a projection operator? I called get next on a projection iterator. How many times do I need to call get next on my input? Okay. So, okay, thank you. If you don't understand the question, ask me to repeat it. Okay, so a projection operator has to, it reads from some vague, fuzzy set of operators. If I want to produce one tuple in the output of this, how many tuples do I need to read from its input? At least one. Or in general, exactly one. The selection operator. So if I'm doing a selection, I have some vague fuzzy input. How many tuples do I need to read from my input here? Sure, it depends on what the selection predicate is. So it'll be at least one. Do I ever need to look at those tuples ever again? So once I produce, once I read one tuple in from, once the selection operator reads one tuple from its input, what happens? It will produce either an output or it'll drop it on the floor. But once that tuple has been read in, do you ever care about that tuple again? No. Same thing for the projection operator. What about a join? So a join operator needs to read in tuples from A, it needs to read in tuples from B. Do I have that same property here? No. Why? So every tuple in A needs to be joined against every tuple in B. So every time I see one tuple in A, I need to do a full scan over all of the tuples in B. So for every tuple in B, I'm going to need to see it at least n times, where n is the size of A. One of the really, really cool things about this algorithm, this particular join algorithm, is that it doesn't actually have that property, assuming that my input is already sorted. How many times am I going to need to see one? Just exactly once. So every single time I can just iterate over the inputs, and I only need to visit every input exactly once. Again, this assumes that the data is already sorted, but in that particular case, this is, so projection is a fully pipelined operator, selection is a fully pipelined operator, and this join algorithm is, assuming that the inputs are sorted, fully pipelined. Okay, so we also talked about actually, before I move on, questions about sort merge join. Yeah?
Just like a little bit of changing the algorithm, could you also have it apply to bags?
That's a great question. So what would you need to do to change this in order to make it work with bags rather than sets?
You have to have some type of precedence, so whenever you hold the pointer on the top, like a mini for loop type thing, but then when you get to the next value, then you evaluate then on which.
Okay, so fundamentally what's the difference between sets and bags? What would be different about this picture if let's do this, a little more space. So what are my inputs? 1, 2, 3, 5, 1, 4, 5, 6. Change my inputs into a bag. Give me some example of how that would
go. A bunch of ones before.
All right, let's add a 1 here, let's add a 1 here. My cursor points to 1, my cursor points to 1. What would I need to do now differently? How would I need to change what I'm doing?
You won't be able to remove the ones from the set. You have to wait until you get through.
Okay, so basically I'd have to treat all of the ones, as essentially one entry in this algorithm. Same thing here. I'd have to treat all of the ones as one entry. My pointer points to all of the ones. And I basically can do a nested loop join over call this 1A, 1B, 1C, 1D. What would my output be? A, C, A, D, C, C, B, D. So this is basically just a Cartesian product of the set of ones here, the bag of ones here, the bag of ones here, and I can compute that by doing a nested loop join over all of the matching values. Great observation. Does that? Any other questions? All right. So we briefly touched on external hash join. So the idea here is that you scan through all of the records on A and build a hash table over those records. You scan through all of the records of B, build a hash table over those, make sure your hash tables line up, and then for every bucket in each of the hash tables, you do a nested loop join over the elements of that bucket. So in this case, all of the ones fall into the same bucket. You can do a nested loop join over there, produce a one. You do a nested loop join over all of the other buckets. Eventually, you get to another bucket where there's an output, and you produce your final result. Questions about external hash join? All right. Now, there is an observation that this wasn't necessary. You didn't necessarily have to go through all of this trouble. If you could keep the entire hash table in memory, the entire hash table for one of the two relations in memory, you can build a hash table for that one relation, and then as you're scanning through the elements of the other relation, you can join those elements against the elements in the hash table that you've just created. So one joins with one. 1 and 2 might fall into the same hash bucket. 1 doesn't join with 2. 3 doesn't join with 4. 5 joins with 5, and 6 doesn't join with 5. So again, you're doing a little bit of organizational effort. You're organizing all of the elements of A, and then as you're scanning through B, you can look up the corresponding elements of A. Yeah. The other. Okay. So if you're doing a join, and let me restate. So the question is, what happens to the other values? The 6, the 4, so if we're doing an equality join, and I'm specifically focusing on equality joins here, back up. So if I was doing an equality join, what would my output here be? Or I am doing an equality join. So I'd like to find all of the elements of A that have a corresponding element in B. 1 and 5. So as I'm scanning through the elements of A, so essentially what happens to the 6 is that the 6 in B doesn't have a corresponding element in A. Does that address your question? Where would the value be stored? I'm not sure I follow. Could you? Okay, I think I have a sense of what you're asking. Let me draw an example on the board and see if I follow what you're asking. So you're doing a join, and you have some relation, which is an attribute. 1, 2, 3, 5. And you have another relation, call it S, which has its own set of values, 1, 4, 5, 6. So there's an array here. There's an array here. Now, the goal of this operator is to produce a new array, a new set of outputs that, as you said, should contain R join S that should contain 1 and 5. So an implementation, so I've been describing a couple of implementations of algorithms that can help you get from these two arrays to this array. Am I on the right track here, or?
I mean, I get the output. Just like, I'm just wondering, like, with the other value, you just
So what happens to this array after you've computed the join? I see. So that depends on how you got this. So the kind of cute thing about relational algebra is that this could arise in a couple of different ways. This could be a CSV file, in which case I'd call that CSV file S. This could also be, let's say, two CSV files. If I take one CSV file and concatenate it with another, this could be S and S prime, union together. So I have S is 1 and 4. Prime is 5 and 6. And I union these two together, I get another array, or another iterator of an array, since you don't always want to create that. The CSV file doesn't go away. But as you're computing the different stages of the query, in general, you don't want to keep results around once you're done with them. Does that address your question? Yeah.
Why make the hash table size 3, not like 6 or...
Example. So the question is, why did I choose a hash table size of 3 rather than anything else? The rule of thumb in general is that you want a hash table that is, I want to say, that has the square of the number of elements that you have. Can't be right. Actually, there's several rules of thumb, each contradictory. In general, this is the choice of a hash table size depends on what you're trying to accomplish. And in this case, I'm trying to accomplish an example where two things hash into the same bucket. In general, you would want to pick a hash table size so that nothing hashes into the same bucket. That's usually some constant factor bigger than, that's a number of hash entries that is some constant factor bigger than the number of elements you have. But hash tables are a bit of a black art. I don't have a really good answer for you there. I know that doesn't exactly address your question. Does it get as close as I can to addressing your question, or is there some clarification I can make?
Then how you increment like 1 and 2 be used 1 array, like the spot, and then 3 will be 1 spot, and 5 will be 1 spot.
I see. Okay. So for the most part, okay, so for implementing hash, there are two answers I can give you here. The proper answer is you open up your data structures textbook and see that a hash table is actually not a list of buckets, but every bucket is actually an array of elements. So you actually put things into the arrays and so forth. In practice, implementations of hash tables do this for you. So, for example, a Java's hash table or hash map implementation does this automatically. It will create a set of buckets, and if two things fall into the same bucket, then it will automatically use the equals operator to figure out whether it'll store both elements in the same bucket, and it'll use equals to distinguish between them, essentially performing an nested loop join for you. So the pragmatic answer is that most existing languages have map implementations or have hash table implementations that hide this already. I'm showing it to you here because you should understand how, you should understand the underlying idea, but for the most part, this will get implemented for you. Does that address your question? Anything else? Sure. So you build up the hash table, and then so one hashes to the first bucket, and you basically want to find all of the ones that fall into the first bucket. 4 hashes to, I believe, the second bucket. You want to find all of the 4s that match, that are in the second bucket. 5, so forth. So does that? Any other questions? All right, so the last thing is the last join algorithm assumes that you already have an index structure built up. So if you have a hash table already built, if you have a a hash index or a tree index already built up, you do exactly the same thing, except now you don't actually have to build the hash index. You can just iteratively retrieve the specific elements that join against what you're trying to, that join the specific elements of, in this case, B, that match up against the elements of A that you're scanning over. So you visit every element in A exactly once, and for every element in A, you find all the matching elements in B. Yeah?
Under what condition would you already have that built? Isn't that just a preliminary stage from the earlier algorithms you just talked about?
So the question is, under what conditions would you already have an index built? Well, what if you had a query that you kept asking? Like if I said, I am going to, for the next week, every day I'm going to issue 1 million queries asking about which classes students are taking. If I was doing that, it would make sense to, even before I answer the first query, build up an index. And then I have that index for the rest of the 1 million queries for the day or the week. And so a database typically will have not just the base data, but it'll actually maintain, build and maintain indexes over that data that help you answer queries. We haven't gone into this quite yet. Not sure if we'll get into this in the depth that I'd like, but usually, pretty much every database system has a mechanism that will kind of help guide you to, that'll keep track of what queries you're asking, and that will suggest index structures that can help make those queries run faster. We'll actually get into this with Project 3. You'll have, so in Project 3, in addition to answering queries really fast, you'll be given about a minute or so of pre-computation time that you can spend doing whatever you want. One of the things that you could do during that pre-computation time is build indexes so that you can answer the following queries even more efficiently than you're already answering them. A little bit roundabout. Does that address your question? All right. One more. Okay. Wow. took up a fair bit of time. All right, so I've just given you 6 different join algorithms. Why do you need 6? Why, I mean, isn't one good enough? When would you use one algorithm or the other? What's my generic answer to everything?
It depends.
Okay. We're paying attention. Good. So what does it depend on? Space complexity. So the different algorithms have different space requirements. What else? More data.
Your data.
Expanding on that, how data is organized.
Okay. So So how's the data stored? How's the input data organized? There's another feature. What else?
Personal preference.
Personal preference. That's deferring the answer a little bit, because your preferences are still based on some properties.
Sorry.
Actually, no, that's, now that I think about it, there's actually a compelling reason. So MySQL, for the longest time, implemented only sort, merge, join. And there's a good reason for that that I'll get into in about a lecture or two. Anything else? So one other thing is how much data do you have? So that may be part of what you were saying. So I made this handy dandy table for you. Basically, there's a whole bunch of trade-offs. So nested loop join can be so the pipeline column basically says, do I need to see any tuple more than once? And then there's basically three different versions of this. Either I need to see tuples more than once, in which case it's not pipelined. I need to see tuples from one of the 2 relations exactly once, in which case it's half pipelined. Or in the case of sort merge join, as I said, if the data is already sorted, I don't need to see the tuples more than once. Memory requirements. So each of these algorithms has different memory requirements. Sometimes it's constant, sometimes it's a fixed amount of memory based on the size of either of the relations. Sometimes it's actually you need to store everything in memory. And then the last constraint, and this is something we didn't bring up, what kind of joins can you actually perform? So the join is on some sort of predicate. You're asking for some subset of the tuples that appear in the cross product. And each of these joins has a slightly different, works for a slightly different type of predicate. So for example, nested loop and block nested loop have no limitations whatsoever. I mean, you're producing every single tuple in the cross product and testing it one by one. Doesn't matter what test that is, you're going to be able to implement it. An index nested loop, well, this depends on what kind of predicate are you allowed to use there. Well, it depends on what kind of indexes you have built. If you have an index that can answer a specific predicate, like a tree index, and you're trying to find a range, then index nested loop will work. And the others will only work for equality predicates or equijoins. All right, questions so far? Yeah.
Does this imply that MySQL used to not be able to join on more than just an identity?
Well, let me rephrase what I said. It implements block nested loop and sort merge. Sort merge is the only interesting / efficient join algorithm that it implemented. All right. Let's take a quick 5-minute break, and then we'll move on to actual optimization. I'll be back here at 1:05. Alrighty. So some of you may recall this picture from a couple of lectures ago. The basic flow of the basic control flow of the program that you're working on as a project. You start with a SQL file. The SQL file gives you some select and create table statements. The create table statements give you a schema. You can use the schema to generate a relational algebra tree or an iterator tree. Use that to read from your data files and produce an output. Now, this is where I find this is the part of databases that I really find exciting, because relational algebra is this really simple, really straightforward language that you can reason about very easily. And what that allows us to do is take one relational algebra tree and find another relational algebra tree that looks exactly the same, or sorry, that does exactly the same thing, but actually does something, the way it does it is potentially completely different. Now, in order to reason about this properly, we need to have some way of justifying to ourselves what equivalent means. So, I have a simple example here. I don't know how many of you follow Star Trek, but there's a character called Spock. And there's a couple of different variations of Spock. So you've got Spock in the original series, who does not have a beard and is played by Leonard Nimoy. And then there's the evil version of Spock, who, as per the trope, has a beard. This means he's evil, and this means he's different. Now, also, more recently, and this is where it gets a little more fuzzy, the series was completely remade, and they had a different actor play exactly the same character. So this Leonard Nimoy and Zachary Quinto are both playing the same character. In some sense, both of them are equivalent. They're the same entity. And what we're trying what I want to get across here is that you can have two different things that look the same but are actually producing different results, or you can have two different things that look different but that are actually producing the same results. And what we're going to look at today is this idea of equivalence, defining equivalence precisely, and coming up with ways of finding queries that are equivalent and recognizing that one of those two is better. And if we can do that, if we can find that x and y mean the same thing and y is better, anywhere we see an x, we can replace it with a y and make things go way, 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 way faster. All right. A couple of simple examples. So here's some data. I've got R and I've got S. So first off the bat, is the expression R equivalent to the expression S? No. I mean, they have different schemas, they have different data. Doesn't make sense. What if I project things down? Oh, whoops. What if I project down to just the attribute A? So is the expression R equivalent to the projection of A on the expression S? No. Well, not for this data, but at least we're a little bit closer. We have the same exact schema. So the projection of A gives us something with the same schema. So at least it's a little closer to being equivalent. Another one, what if I project not just A, but if I take A and replace every value of A in S with a value that's one lower? Is that equivalent?
Yes.
Yes, but? So is that equivalent in general or just for the specific data set? Just for the specific data set, good. What about if I just took every element of R and incremented it by 1? So for this specific data set, those are the same. So I'm gonna give you two definitions. They're essentially the same, but that mean slightly different things. And we're gonna focus on one of them. So I'm gonna tell you that two expressions are equivalent if we can prove to ourselves that they produce exactly the same output. So I gave you a couple of examples with exactly the same output on specific data sets. What we'd like to do is generalize that. We'd like to come up with a way of proving to ourselves that two expressions produce exactly the same output on all data sets. Now, there's a bit of a gotcha here. And anyone care to take a guess on what that is? So what exactly do I mean by the same output? How do I test whether two things are the same? Yeah?
Like produce the same output, but one could run faster than the other, and get twice as many steps as the optimal.
Okay, so there's performance. At this point, I don't care about performance. Ideally, I'd actually like to find something that's equivalent but faster. So performance is not going to be part of our definition of equivalence. Order, okay. What do we, expand on that a bit?
Like whether or not things might not be equal, or they might be equal depending on which notation or order scheme, whatever one you're using. If the order is the same or it's not the same.
Okay, so order is one thing. More generally, which semantics are we using? So is 122 the same as 212? Order is, so are we using list or bag semantics? Is 112 the same as 12? Are we using bag or set semantics? So we need to be clear about this, and I'm going to talk almost exclusively today about bag semantics. So we're going to be looking for equivalence under bag semantics. We don't care about order, but we do care about count. Different things hold depending on which types of operators you're using, what the output of the query is expected to be. In general, you probably want to be looking at list semantics, but there are, that only comes up with one operator. We'll get to that later on. So for the most part, we're going to be talking about bag semantics. Now, relational algebra is nice and simple, and that simplicity allows us to define some properties. Question. Has anyone taken algebra? And I don't mean like high school algebra, x equals y plus 2. I mean like serious algebra, set theory, rings, semi-rings. Person, 2, okay. All right, so have you heard the term commutative? Yes, okay. Have you heard the term associative?
Yes.
Okay, so these are properties of operators in an algebra. And we can define a number of these properties that are essentially, these properties basically say that one expression means the same thing as another expression. So one thing that's already been mentioned in class is this idea of selection being decomposable. So if I have a selection operator, C1 and C2, I don't care what's in here. I don't care what's up here. Let's call this A, let's call this B. I don't care what's up there. I don't care what's down there. But that and 1, those two are completely identical. If it has to fulfill both C1 and C2, the condition C1 and C2, then I can filter out everything that doesn't satisfy C2, and then afterwards I can filter out everything that doesn't satisfy C1. Why would you do this? You'll see in a moment, but does everyone buy that this is a legit thing to do? All right. Does anyone not buy it? Proof by intimidation. All right. All right, so it's also so it's also decomposable. What do I on ors? This one's a little bit weirder, but if I have C1 or C2, then I can take, actually that's not entirely true, but if B is producing a set, then this is essentially equivalent to under certain conditions, if I were to do a bag union of under set semantics, this would be equivalent. One other interesting property is commutativity. Now, here's something I'd like you guys to do, or at least guide me through it. So if I tell you that selection is decomposable, can you prove to me that it's also commutative? Decomposable on AND. So I have okay, so there's something to do with the commutativity of AND. How do I actually get there?
So you just use a commutative property to flip the AND on the left side, and then you'll get C2 outside and C1 inside. And then
how do I get from missing one step? How do I get from here to an AND? Raising your hand. Yeah.
I suppose you could just say, so for the community part, if you take the first one, that would be equivalent to the selection of C1 and C2.
Ah, okay, so these work backwards too. Excellent. Double the number of properties. So this whole thing is equivalent to what? C1 and C2. Sweet. Okay. Now I can use your trick. This is equivalent to, by the associativity, the commutativity of AND C2 and C1. And that, bring it home.
C2 on top, C1 on
Great, we've proven a new property. This, I think, is extremely cool because you can take really simple concepts, really simple ideas, and by algebraic manipulation, you can get to more complex and more interesting properties. Now, earlier I told you translate simple, optimize smart. This is exactly what I mean. If you can translate something into a really simple form, you can use equivalencies to come up with a much more efficient version of it. Okay, so two other things here. So projection is idempotent. If I project down to a small set of columns, it doesn't matter if I projected away a smaller set of columns, So I have projection down to A and the attributes in A and the attributes in B, and then I project that further down to just the attributes in A. That's completely identical to just projecting down the attributes in A. And note that this works backwards. I can also add attributes. I can add new projections safely. Cross product is associative and commutative. This is also a nifty, property. Let's do another quick exercise. Can you prove to me that R cross S cross T is equivalent to T cross R cross S? Remember proofs from high school algebra? Should be ringing some bells here.
Set that equal to R cross S cross T.
R cross, so what property are you applying here?
Of the associative property.
Okay, so I can change the parenthesization of R, S, and T. So I can turn this into R cross S cross T. All right, cool. And that's it. Well, we're one step away, so we're at R cross S cross T. Yep.
We could use S multiple T, could we think about another letter, for example B, and then R multiple B, which is equal to B multiple R. So we switch the B to inside to the R to the B, and then after that sentence.
Okay, so we can kind of hide what's in there. We don't actually care what's in here. What we care about is the fact that some blob cross some other blob, let's call this A and let's call this B, this is entirely equivalent to some blob, let's call it B, where that's the same B, cross some blob A. So associativity gives us that this is equivalent to T cross of R S. All right. Okay, so these are kind of the basic building blocks that we're working with. Now, there's also different types of interactions that we can talk about between different types of operators. So let's take a look at some of these one at a time. Selection and projection. So selection, and I'm going to put a little caveat on this, but selection and projection in general commute. The catch here is that the projection operator only commutes if you're not projecting away any attributes that are in the selection condition. In other words, you can only, if C depends on some attribute that you're getting rid of, this doesn't work. But assuming that that is true, then selection and projection commute. So let's actually try and use this. So let's put in a start and end point here. So what I'd like you to show is that I have projection down to some set of attributes A, and I have some condition C that I'm going to say is compatible with A. I'd like you to show me that this is equivalent to the projection of A sitting on top of the selection of C on top of a projection of some new attribute A and some other set of attributes B that contains the columns of C sitting over R. Start point, end point.
So you have this hiding the middle, projection A, union column C, and
Okay,
then
so
for
what's the next step?
We select R,
Hmm?
select CR. Outside is projection A union column A union.
Oh, I see. So R, C, okay.
And then projection A intersection of union.
Union.
Okay.
Sorry, did I put a?
Union. So A union B. And then outside is still projection A. So then
Am I allowed to do that? So
using the top one.
how does so? Seems like you changed this projection operator. What allows me to do? What allows me to split it like that?
From the top one, this seems the union projection A can select C. So I'm going to selection C then do the union. Outside is still projection A. I didn't change that all.
So yeah, it looks like this whole segment is unchanged. You kind of treat this as, just for the purposes of this, just a black box. That rule up there talks about selection, so are you sure you mean that rule or idempotent? Okay, so projection is idempotent. I can introduce as many projections below another projection as I want, as long as they don't, as long as they have at least the set of attributes that are in the outer projection. All right, so I got one equivalence, sure, not quite all the way to the end. Let's do a little dance or something. A little voodoo dance to get the middle step. Yeah. Oh. All right, so projection and selection are always commutative as long as all of the columns in the selection predicate are referenced in the projection. And that's definitely the case here. So we're allowed to swap those two. Great, and that's what we're going for. Perfect, yeah.
Doesn't this seem like kind of a risky generalization to make, seeing as, I don't know, unless you have, at the time that you're rearranging this, you have all of the relational algebra you're going to need to use, correct? Or could you potentially need something later on that you're going to cast away and not realize it?
Are you going to need something later on that you might be casting away? So here's, I'll put this question to you. So yes, you do kind of, you don't necessarily care, so this whole thing defines a new relation, right? What's the schema of the relation that this defines? That this expression. What is that? What's the schema there? A. Yeah. So it's just the attributes here. So it's completely true that I could have some query sitting on top of that. Let's say I'm trying to join that with some other table S. But if I add a new projection operator here, am I actually changing anything about the output of this? Is that going to do anything? No, it doesn't change anything in the output of this. From the perspective of the outside world, this remains unchanged.
Okay, I guess my question is, based on the condition that A must include all columns referenced by C, how often is that actually satisfied?
How often is that actually satisfied? So,
How many cases are we going to find where, if we were to consider these to be equivalent, it would no longer work?
I see. So in general, this particular condition actually arises mostly because you want to push projections further down into the tree. So something like this is usually followed up by one of these flips. In that case, you can actually choose. Let me rephrase that. So I'm giving you kind of a primitive, simple property, and we came up with this slightly more complex property. So anytime I have a projection, I can introduce a new projection that keeps a specific set of columns. That, in and of itself, might not necessarily be all that useful. This, on the other hand, ends up being quite useful quite frequently. Does that address your question?
Yes, thank you.
Random question. When would that be useful? Think about it. We'll get back to it. All right. So here's another one. Selection and cross product. Well, we've already covered the basic idea here. A selection plus a cross product is a join. Now, there are limitations on what kinds of joins you can implement efficiently. In other words, if we don't have a good join algorithm that can handle some condition C, this is kind of useless. But this is the definition of join. So let's keep building up our repository of composite cases here. So I've got a selection predicate here. R B equals SB, and R A is greater than 3. This thing is on top of the cross product, which is crossing R and S. Let's say we wanted to turn that into a join. How would we do that? Sometimes helps to start from what you're trying to accomplish. Yeah.
We can just split the two selections since it's not a separate, like there's one selection already.
Great. All right. So first, which one goes on the bottom?
The RB equals the S.
All right. So I can take that selection predicate. Associativity of selection gives me the ability to pick which order I put those in. And R B equals B, and I got my cross product, R and S. All right. Take us home. Someone? Yeah.
You can combine the select statements.
Yes. You can take those two and based on the definition of join, you can combine those two into a join on R dot B equals S dot B. All right. Cool. So we just created a join. We've gone from a selection sitting on top of a cross product and created a join. Am I the only one who thinks this is really cool? Different tastes. One reason you should think this is really cool is that this optimization right here is going to make your lives ridiculously simpler. Whenever you build, as I keep saying, when you translate from SQL to relational algebra, you can translate in as dumb a way as possible. You don't need to create the joins right then and there. You can translate the SQL statement as a cross product, as a set of you can translate the from clause as a set of cross products. Because you're going to be doing some optimization anyway, it makes sense to build your joins during the optimization phase. This is going to make your code simpler, it's going to make it cleaner, and it's going to really reduce the amount of cruft that you have in your translation code. Oh, come on, someone thinks that's cool. Yes, okay, thank you. So, all right. Okay. Another nice optimization is the fact that projection can typically be pushed down through a cross product. The caveat here is that you need to know which attributes come from which sides. But if you know which attributes come from which sides, which you typically do, then you can always push down the parts of the projection that apply to the left-hand side down to the left-hand side, and the parts of the projection that fall to the right-hand side. Another example. Prove to me that the projection of A on join with condition C of R and S, prove to me that that's equivalent to, that I can push that selection down. So how do I even start this? Do I have any rules for joins so far?
Just break down the join to cross product.
All right, so I need to prove to myself that I can do something with join. If I want to do that, I need to split it up into a selection and a cross product. All right. What can I do now?
You can switch to
Just point, tell me.
You just like search them and then push them in the project projection.
All right, so I have a rule that tells me that I can swap the order of projection and selection. Is that universally true? Okay, so this will only work if that set of columns is sufficient, covers all of the columns that are in the selection. So assuming that that is true, I'm going to put a little asterisk here. So assuming that that is true, then I can swap the order of the selection and the projection, again sitting on top of the cross product, and finish this up. I can push the projection down based on that equivalence. And one last step.
Join this.
Right, and then I can rebuild the join. So I kind of disassemble the join temporarily, just long enough to prove to myself that I can actually push the projection through. And important thing, in doing so, I was able to catch this condition, this specific condition when that projection was when that projection held. All right. Let's see. Yeah.
So, with projection, you said that you have to tell like which one belongs to which one. Is that really necessary to care about? Because if you project a column that isn't really there, does it really matter?
If you project a column that isn't there, does that matter? It will when you're implementing it and you get a null pointer exception because Java thinks that there's a column there that doesn't exist. Also, just in terms of correctness, when you're writing relational algebra expressions, you usually want to create sane relational algebra expressions. The output schema here is going to be A. So if I do a projection, if I project R down to A, and R doesn't include an attribute in A, that means that I have this new attribute that I don't have a value for.
Well, like if you did the projection still at the top, and then just kind of like also did the projection.
Yeah, so you can, basically what value do you give there? Yes, you could introduce new columns, you could give them null values.
I was just kind of saying, instead of trying to like figure it out, like just kind of ignore it and hope it goes away.
Yeah. So that the main argument against keeping additional columns that don't actually exist, or my main argument against that, is that the main reason that you'd want to push projection down is to get rid of columns. And if you're getting rid of some columns and then adding a bunch of new columns, you're not really reducing the amount of data that you're working with. So if I remove columns, then I have less data to work with, and I always like less data. Less data means I have less work and I'm lazy. With more, if I introduce new columns, now I'm giving myself more work. And again, I'm lazy. The database is lazy. You don't want that. Does that address your point? All right. All right, so one other observation is that both union and intersection are both commutative and associative. Selection and projection both commute with union and intersection. You can always push a projection down through a union. You can always push a selection down through an intersection. I'll leave the proof of this to yourselves. So let me do, in the last 5 minutes of class, let me go through a really high-level example that could show how you would actually use these ideas in practice. So I have a simple select query here, a SQL query here, and on the right I have the relational algebra tree that I would get by that I would get out of that query. So I've got a projection. I only care about RA and TE. I have a selection predicate. I want only those R's. Those rows of R where that match the rows of S on B, and I only want those rows where the SD attribute matches the TD attribute. And I also have a predicate on SC. So what can I do here? So I can split up that selection. How would I split it up? So, kind of intuitively, what am I trying to do here? I'm trying to create as joins in principle. So I'd like to at least pull out the RB and SB. Oh, sorry, the SD and TD. One other property that I may have jumped over, is that I can always push selection into a cross product. If, as long as I push down the select, as long as all of the attributes in the condition come from one of the two relations. So in this case, am I allowed to, is there any way that I can push part of this selection down into one of the two sides of the relation? Yeah?
You could put R dot B equals S dot B into the cross product of R and S.
Okay, so I can push that down to the left-hand side. Anything else? Yeah?
Pull the S dot C down there as well.
All right, so basically I can split, anytime I have a selection sitting on top of a cross product, I can split it up into three parts. The parts I can push down into the left-hand side, the parts I can push down into the right-hand side, and the parts I can't do anything with. And then going step by step, I can, well, split it up, and then I can further split that up to push the selection, different selection operators down into each side. So far, everything we've done is simple transformations that we've proven to ourselves don't actually change the meaning of the output, the meaning of the query. We can do exactly the same thing all over again once we're down here. We can take this, so we can take the selection sitting on top of the cross product, that becomes a join. And we can take the selection predicate sitting on top of the cross of R and S, and once again we can do exactly the same thing that we did before. We can split that up into two parts. The part we can push down into the right-hand side, and the part that we can't do anything with, at least not immediately. Now that we pushed the, then we can push the selection on S.C into the right-hand side of the cross product. Can turn the cross product into a join, and we've come up purely by using little local rewrites on this tree. We've gone from a really expensive plan, a complex but easy to translate plan, into something that's way, 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 way more efficient to evaluate. All right, so any questions on the example, or? So I'll leave you with one basic, with the thing that I keep harping on. Don't try and translate, don't try and optimize the translation. Optimize after you translate. Find patterns and replace the patterns with more efficient patterns.
Yeah.